This is ISCI 2001, Chapter 15, Earth. The themes for this lecture includes two major subdivisions. The first is Earth's materials, which includes minerals, rocks, and the rock cycle. The second subdivision is Earth's interior, which is the crust, the mantle, and the core. Earth's materials. The Earth is made up of various chemical elements that are unequally distributed and found. There are 8 elements that make up 98.6% of the Earth's crust, whereas oxygen is 50%, silicon is 25%, and both oxygen and silicon together make up 75% of the Earth's solid surface together. So that's quite a significant number, with oxygen being half, silicon being a quarter of the makeup. A mineral is a naturally occurring, non-synthetic, inorganic, solid element or compound with a constant chemical composition in a crystalline structure, which is a crystal shape with atoms in repeating or regular patterns. The key word for inorganic, inorganic means it does not contain the element carbon. Anything that is organic contains carbon, such as we are carbon-based life forms. One of the major components of humans is carbon, as is plants, fungi. Any of the 6 kingdoms are carbon-based, so we are considered organic. So if you ever take a class like organic chemistry, you'll be looking at the chemistry that is dealing with the element carbon. So don't get this confused with the mainstream organic, like in our supermarkets, that kind of stuff. This is not the same type of organic. The organic in our supermarkets just means that it wasn't made with pesticides, insecticides, or anything unnatural. Whereas in science, when you talk about organic, it is strictly talking about things that have carbon in them. Now, the crystalline structure, like I said, it is a crystal shape. You'll be seeing a picture in just a minute of the different atoms in repeating regular patterns. But this would be like salt. If you look at salt underneath the microscope, it's a cube. Whereas if you look at sugar, it's a jagged crystal, and neither one of these have carbon in them. Here's the crystallitis examples of the crystalline structures. It's got the elements listed beneath them. For some examples, like our cubic body centered, which is like our square. You'll see that in iron and several other of the elements. With the cubic face centered, this is a more sturdy, I guess is the best word to say it, sturdy, cube shaped. You can see the different elements, or the different atoms that hold it together, and it makes it more like a webbed structure, so it makes it stronger. And this includes like aluminum. You know, the airplanes, the outer metal of the airplanes is aluminum, and it's very, very thin, versus with it being iron. If it was the cubic body centered type with iron, number one, iron would be too heavy, but if you get it down in a very thin sheet like you can aluminum, it's not going to be as strong. Then you've got the hexagonal shape, which is titanium, things like that, and they are super, super strong. So you're looking at the cubic body centered is the least, well, I wouldn't say the least strong, because it's still strong, but it's just the lesser of the 3. Cubic face is about a medium grade of strength, and then the hexagonal is your strongest. Like I said before, silicon and oxygen are the most common minerals, and all the minerals are classified on the basis of if they contain these 2 elements or not. You have silicates, and then you have non-silicates. Silicates are the most abundant mineral. They make up 92% of the Earth's crust. Non-silicates make up 8% of the Earth's crust. So silicates are definitely more common than the non-silicates. Silicates are subdivided based on if they contain iron and magnesium. So you have the ferromagnesian silicates. This is your olivine, augite, hornblende, and biotite. These have a greater density and a darker color due to the presence of the metals. Your non-ferromagnesium silicates, like muscovite, like white mica, the feldspars, and the quartz, they have a lighter color and a lower density. And these words that you're seeing, olivine, augite, hornblende, biotite, muscovite, white mica, feldspars, and quartz, these are all names of minerals that you can find. They look like rocks when you first find them, but they're actually minerals and not rocks. So here's a picture of them. I love the olivine. It's very pretty. It's a nice green color. Then you have your augite, hornblende, and biotite. The biotite actually can chip off in layers, very, very thin layers that are paper thin. Then you've got your hornblende and your augite. Now, when you look at minerals, you can look at the hardness of the minerals, of how hard they are. And of all of these on here, none of them are super, super hard. They're pretty easy to break or chip. Then you've got your muscovite, your feldspar, and your quartz. Your muscovite is similar to the biotite as far as you can flake it off into very, very thin layers. Your quartz, these are the quartz crystals that are commonly used in watches. And then you have your feldspar. Feldspar is really cool when you touch it. It actually, it's hard, but it feels really silky. It has the texture of it is very unique, and it's really nice to be able to feel the silkiness of it. Your non-silicates have 8 groups. You have carbonates, sulfates, oxides, sulfides, halides, phosphates, hydroxides, and native elements. And with all of these, they're not as common. It's harder to find these. Remember, these only make up 8% of the total mineral population of the earth. Here are 2 examples of carbonates. You will find them in different colors depending on where they're found, what's found around them. You can see the carbonate on the left has a blue tint to it. The carbonate on the right is more of an orange or a rust tint. Sulfates are absolutely beautiful. You can get turquoise color all the way to solid white, but if you look at the crystal formation on them, they can be various, like I said, depending on where they're found and what type of weather or climate is around them. But if you look at the one on the right, it looks almost like ice that's been chipped, but it's very beautiful. Oxides are like your carbon monoxide, your magnesium oxide, which is perclase, your silicon dioxide, which are called emeralds, and then you have your aluminum trioxides, like your corundum. And if you look at, well, you can see carbon monoxide. We all know that that is a gas, and that is very toxic to humans. And you have your magnesium monoxide, which is the perclase, and it is found in this cube structure. That is its actual the word just completely left me. Your cubic face. Okay, whenever we were talking about the lattice, the crystalline lattice, there we go, came back. That's your perclase, and that is, it actually does make a cube. Your emerald, which is also called silicon dioxide, it is in a hexagonal shape. It's very strong, and it's got that nice green color. And then you have your corundum, which is your dialuminum trioxide. Sulfides. When we look at sulfides, it almost reminds me of the old Superman movies with the kryptonite and the place that he came from that has all the crystals around it. That's kind of what it reminds me of whenever I see it. But they're very shiny, metallic looking. Then you have your halides. Once again, they come in different colors depending on where they're found. They can look almost like a mossy green, or they can look. They can have the red with the white on the outside that looks like ice, but it's actually not. It's actually the outer covering of it, and it's very pretty. Phosphates. These are the kind of phosphates that we use to preserve food. Your nitrogenous phosphates and that kind of thing, as far as not not what I would suggest to use for food preservatives. It's also what can be found in washing detergent. So be very careful whenever you're looking at food and what it's preserved with. If it's preserved with phosphates, this is what a gaseous form of this is what it's being preserved with. So just keep that in mind. But it can range. It has a wide variety of colors from clear all the way through yellow, but it will be transparent. Then you have your hydroxides. You can see with the picture on the right, it kind of looks really gross, but that is a liquid form of the hydroxide. It's a byproduct. And then on the left, you can see the actual mineral there. So a lot of these do have different uses in the human world, not just in the solid form. You have your native elements, and which are metals and nonmetals like gold, silver, diamond, graphite, sulfur. You all know, what we use all of these for. Obviously, gold, silver, and diamonds, we use those in jewelry. Your graphite is what is in your pencil lead. The actual lead of the pencil is straight graphite. And then sulfur, we have a sulfur plant here in Bainbridge, Georgia. But they use that for a lot of different things. One, just off the top of my head, is in matches. It's when you strike a match, that smell that you get when you strike that match, that is, you're smelling sulfur. Now, shifting from minerals to rocks. Minerals and rocks are not the same thing. Okay, rocks are elements. The elements are chemically combined to make minerals, which are physically combined to make rocks. Okay, so if it's chemically combined, it makes minerals. If it's physically combined, it makes rocks. So I'm going to describe in the next few slides exactly how these rocks are made. Okay, a rock is defined as an aggregation of one or more minerals and perhaps other materials that have been brought together into a cohesive solid. So whereas a mineral is going to be typically one element, a rock is going to be at least one of those minerals or more that are combined, and it's they're combined through physical means like pressure, heating, cooling, that kind of thing. So once it has been made into a rock, it is a rock. It is no longer a mineral. Rocks are classified into three main groups. You have igneous rocks, sedimentary rocks, and metamorphic rocks, and these are the three types of rocks that make up the rock cycle. Igneous rocks are formed as a hot molten mass of rock where the rock is cooled and solidified. So number one place that you would get igneous rocks would be from volcanoes. Sedimentary rocks are formed from particles or dissolved materials from previously existing rocks. So when you look at the different strata layers, which you'll see a picture of in a few minutes, you'll see how it is how the sedimentary rock forms layers, and it looks very layered. You can definitely tell. Then you have metamorphic rocks, which are formed from rocks that are subjected to high temperatures and pressures that deformed or recrystallized the rock, but it didn't melt it completely. Okay, and this is formed usually from being deep within the earth. All of the pressure and the heat that just comes from the friction of being way below the surface of the earth. So here you have your igneous rocks. On the left, it's magma or lava. As it cools, you see on the right hand side, that was from a lava flow, and then on the bottom, that's what the rock actually looks like once it is completely cooled down. Sedimentary rock, you can see the nice strata layers in the picture on the left. This includes limestone, which we have tons of limestone right beneath our feet. We have chert, we have arkose, we have shale, sandstone, and conglomerate. All of these sedimentary rocks do tend to weather pretty easily, which means through wind erosion, water erosion, they can chip away. The earth that is on top of limestone, this is where a lot of sinkholes form, because since we do have an underwater aquifer, which is where our water table is below the earth, where we get all of our water from, it weathers away this limestone. And this is another reason why, if you're, especially if you're on well water, you can get the lime stains on your sinks and bathtubs and that kind of stuff. Is because as it weathers this limestone, the lime actually leaches into your water. Now, it's not going to hurt you, but it will cause some stains, especially to porcelain. Then you have your metamorphic rocks. You can see how bright and shiny it is. It looks wet, but it's actually not. It's just that shiny. On the picture on the left, you can see the red band that's going down is your metamorphic rock. And there is lots of pressure within the earth because of tectonic plates and because of how they shift. There's lots of friction. So you can have either sedimentary rock or igneous rock. Either one of them can be turned into metamorphic rock. Now, speaking of turning into metamorphic rock, the rock cycle. Internal changes alter the Earth's surface by moving the continents and building mountains that are eventually worn away by weathering and erosion. The seas advance and retreat over rocks, and the rocks are transformed from one type to another through these continual changes. The concept of continually changing rocks through time is called the rock cycle. This is just a basic picture of how the rock cycle works. It typically, when the Earth first was made, it was igneous rocks because it was very, very hot. But those igneous rocks can do two different things. Well, actually, three different things. They can melt and reform into igneous rocks is the first thing. Through heat and pressure, they can become metamorphic rocks. And through erosion and deposition, they can become sedimentary rocks. So as they're worn down and eroded, they'll form another rock layer over time with pressure, and it will actually cause the sedimentary rock to form. Now let's look at the sedimentary rock. And with sedimentary rock, you have a couple of different things that can happen, or a few different things. First of all, it can erode and deposit on the Earth's surface again and become sedimentary rock again. Or through heat and pressure, it can become metamorphic rock, or through melting can become igneous rock. The third is metamorphic rock. It, just like the other two, it can reform into itself. If there's enough heat and pressure, it can reform into another metamorphic rock. If it is eroded and deposited on the Earth's surface, it can become sedimentary rock, or if it melts, it can become igneous rock. So the main thing to know is, if it melts, if any rock melts, it's going to become igneous rock. If any rock is eroded and deposited, it's going to be a sedimentary rock. And if any rock is placed under enough heat and pressure, it's going to become metamorphic rock. Okay, so those are your three main distinguishing factors between the three different rocks. Sedimentary rocks are made from erosion and deposition. Igneous rocks are made through melting. Metamorphic rock are made through heating and pressure. The Earth's interior. The Earth's internal heat and rock movement are related to some things that happen on the surface, such as moving continents, earthquakes, and volcanoes. And it also can go towards tsunamis also, because, a tsunami is formed by an underwater earthquake. So, but however, for now, we will focus on the changes that occur internally. The sudden movement of very large sections of rock can produce vibrations that move out as waves throughout the entire Earth. These vibrations are called seismic waves. You can actually get online and Google seismic waves or seismic waves 2012, and it'll actually show you a picture of where all of the seismic activity, the earthquakes, have happened in the past year. The crust is the outer layer of rock that forms a thin shell around the Earth. It is very thin compared to the other two layers. It exists below the oceans, and it makes up the continents. The crust varies in thickness around the Earth's surface, being thicker under the continents and thinner underneath the oceans. The mantle. Below the crust is the mantle. It's a much thicker shell than the crust. This shell makes up 80% of the total volume of Earth and accounts for 2/3 of the Earth's total mass. So you've got the crust, and then just below the crust, remember the crust is very thin, just below the crust is the mantle, and it's a much thicker shell than the crust. So just keep that in mind, and then we'll get down to the core in just a second. The core is the center part of the Earth. This is a nice picture where you can see the inner core, the outer core, the mantle, and then the crust. Look at the crust. That is a very exaggerated thickness. It is really not that thick even compared to the rest of them, but in order for you to be able to see the crust, we had to be able to exaggerate it just a little bit. You can see that the mantle is quite a bit larger than the crust, and then you've got two different parts of your core, inner and outer. Inner core very, very, very hot, and it cools as you get more towards the mantle and the crust. Here's two more pictures where you can see top left-hand corner, inner crust, outer crust. Then you've got your mantle, and then you've got your crust. On the right-hand side, you've got inner core, outer core, mantle, and then your crust also. And this also shows the atmosphere. One thing that you do need to know is the crust and the upper mantle together combined we call that the lithosphere. Okay, so the lithosphere is the crust and the upper mantle combined. So GPS standard lithosphere. The standards that we covered today were differentiate rocks and demonstrate a basic understanding of the rock cycle. Also, we're able to recognize and describe the basic properties and components of the soil. Please do not forget to go online and do your discussion and your quiz. Also, we will be having a test on the next class meeting date, which is Wednesday. It will cover chapters 12, 13, and 15. I hope you have a great week.